Hey guys, hope everybody's doing well. So today we're going to talk about discrete time systems. Up until now, we've mostly talked about continuous time systems, namely systems that abide by continuous dynamics. Um, up until now, we've looked at uh, differential equations. We looked at systems in terms of uh, in the frequency domain and the continuous frequency domain. Um, So we've looked at systems where we have a differential equation. Oops. Make sure that I've got everything set up here. Great. So this is, let's say, a differential equation, right? And then we've looked at such things like solutions to these, how to talk about stability of it, um, all for the case where we have a continuous time independent variable. Right. However, there's a whole other set of tools that we could use for the case where we have discrete behaviors. So instead of a system acting continuously where we need to look at a solution in an analog way, we can instead look at a solution in a digital way. And there's ways to convert a continuous time system into maybe a discretely sampled system. And so I'm gonna present to you a modeling technique to model discrete time systems, and throughout the day I'll talk about ways that you can analyze them, talk about stability of them, because it's similar to continuous time systems but slightly different, just due to how the solutions work out for a discrete time system. So how can we think of a discrete time system? So in continuous time systems, we have a independent variable. So in continuous time systems, we have an independent variable t, right, which is greater than or equal to 0. But if we, instead of looking at the whole solution, so if I draw this here, I'll just draw, actually, let's draw this. Okay, so we have, this is our x of t, and this is our t, right? So now if we have this solution that starts at t equal to 0, with the initial condition, and it evolves, let's say like that. Okay, so we can say that we have a continuous time system here. However, what if we can only sample it at discrete intervals, right? At periodic intervals. So let's say that we can sample it here at t1. We can sample it here at t2. Sample it here at t3, t4, and so on, right? So these intervals, let's say these intervals are defined by this value, capital T. Okay, so then it remains to define that we can say that we can index each one of these time instances by each one of these time instances here by a new variable k. So more specifically, we can define k as a natural number, so it's equal to 0, 1, 2, all the way out, right? And then we can say that t is equal to, if we want to transition this from a continuous time system into a discrete time system. So now we can consider each value of k to be a representative of that continuous variable t. And so that that breaks up the solution into isolated points then instead of a continuum of points. So coming back up to this figure here, then if we looked at the discrete dynamics of the system, we would have a point right here at t equals 0, t1, or k is equal to 1, right? So this would be k equal 1. This would be k equal 2. The next one would be k equal 3, 4, and 5, and so on. Right? Okay. So how do we model a discrete time system? So a discrete time system, one way to model it is using difference equations. It can be modeled using difference equations. And I'm not sure if I'm sure you've seen difference equations before in previous classes. But just to reiterate, a simple difference equation is basically looking at a recursive algorithm that takes previous values of the state and includes it in the next value. Okay, so simply put, we have the next value. You could think of this as like a while loop while you're iterating over a discrete set of indexes, right? Or a for loop. So the next value is equal to a function of perhaps that index and that state k. Okay, so now this would be for the case where potentially for the case where x is just a single. It's not a vector; it's just a single value. You can consider a higher order. So this is the case where we have an order equal to 1 because you're only looking ahead one step, or you're only looking behind one step. So higher order difference equations can be modeled as well. A typical version of a higher order difference equation could be something like a Newton-Raphson method for integrating, where you're looking to basically for the next step, you're looking at 2 steps behind, right? All right, so to look at a higher order difference equation, you can say x at k plus n, so this will be an nth order difference equation, is equal to a function of that index plus x at time k, x at time k plus 1, x at time k plus 2, all the way out to x of k plus n minus 1. Oops. Cool. All right, so just as we did with continuous time systems, where we had a differential equation, a high order differential equation, right, that could define the dynamics of our system. Here we're going to have a higher order difference equation, and we could take this difference equation and transition it into higher order states, state equations, and put it into a state space form. Okay, so to do that, well, one, to guarantee solutions to the system, we need to have initial conditions, right? Just like with continuous time dynamics, for difference equations, you need to have the initial conditions for the basically for everything in this function here. So if you need x of k plus n, you need to have all n minus 1 initial conditions. Okay, so to basically to guarantee a unique solution, we need x x of 0 is equal to x0, x of 1 equal to x1. And we need to find all these out so we can guarantee that a solution exists all the way out to x at n minus 1 is equal to x of n minus 1, sub n minus 1. Okay. All right. Next, we can move these into a higher order state space form. So this could be a state space representation, where if we have this function, oh come on. I don't know why it's broken again. Okay, so let's see. So I'll update it. Stop mirroring. Start mirroring. Ah, there we go. Okay, so backing up a little bit. We just need to guarantee a unique solution. We need to have these initial conditions. Okay. All right. Now we're on track. All right. So state space representation. So basically, for this, we can take this function up here, f, with an n degree system, and break it into a number n difference equations, first order difference equations, just like with continuous time dynamics. We can take an nth order differential equation, and if it meets certain criteria, we can break it into n first order differential equations, right? All right, so we can do this by basically the same thing. We can define x sub 1 at time k equal to x k, okay? We can define x sub 2, do I have enough room here? Yes. As equal to k, x plus 1. We can define x sub 3 as k equal to x of k plus 2. And then all the way down to x sub n of k is equal to x k plus n minus 1. Okay. So now what we're going to do is we're going to look at the next time step ahead of that. So we're going to go this way, and we're going to look at, instead of x1 of k, we're going to look at x1 of k plus 1, right? And then this is going to be equal to x of k plus 1, right? Which is equal to, you guessed it, x2, right? x2 of k. Okay, so we have x of k plus 1, and then we have down here x2, x of k plus 1 is equal to x sub 2 of k. All right, and so now that just follows through. So now we get x2 of k plus 1 will be equal to x3 of k, x3 of k plus 1 is equal to x4 of k. And then we can go all the way down to x of sub n of k plus 1 will be equal to this function up here. Okay, so that'll be f k x1, x2, x3, all the way up to x of n. And these are all indexed by k on the right hand side of this equation. And then with the initial conditions, again with initial conditions of x1 naught is equal to x naught, x2 naught is equal to x1, where these x naughts, x1s were defined on the initial conditions above, right here. And then x n naught is equal to x sub n minus 1. All right, let's look at an example. Next page. Okay, so this is just putting an example of putting a second order initial value problem, discrete time initial value problem, into a state space form, discrete time state space form. So we get x of k plus 2 plus k is equal to k plus xk plus x of k plus 1 squared. Okay, and then with initial conditions, x naught is equal to x1 is equal to 1. All right. So now what do we do? Well, let's define our x sub 1 and our x sub 2. Our x sub 1 is of k is equal to x of k. And our x sub 2 of k is equal to x k plus 1. X of k plus 1. All right. And now we're going to get x sub 1 of k plus 1 is equal to, you guessed it, x of 2k, x sub 2k. And then x sub 2 of k plus 1 is going to be equal to k, right? Plus, make sure that you guys can see, great. Plus x1 of k plus x2 of k squared. Okay, so now if you, as you can see, we have x sub 1 is equal to k, so we just substitute that right here, and then we have x sub 2 of k is equal to k x of k plus 1, and we just substitute it there, and we get this right here. All right. And so this right here is in state space form right here. Awesome. All right, next we'll talk about solutions to linear difference equations. So basically, as we take this system right here, and the example is not linear, right? So we have this x sub 2 squared term here. Well, what about the case where it is linear? How do we define solutions for it?